What's really in the water that you're drinking every day? How do we know that there aren't harmful contaminants? Is there a way to find out? The answer is yes, there is a way to find out. So the purpose of this experiment was to identify unknown molecules detected in a drinking water sample using spectroscopic techniques. This procedure involved analyzing the water samples using a nuclear magnetic resonance spectrometer, or NMR for short. This is the equipment that was used for this experiment, and an infrared spectrometer was also used for this experiment, otherwise known as IR. A piece of equipment known as the diamond ATR was used along with the IR spectrometer, shown here. And this specific experiment used samples 99969 and 05024, as well as vial number 43. So sample 99969 was found to most likely be the compound paraxylene. Sample 05024 was matched with ethanol, and vial number 43 was found to be methanol. To begin the experiment, first we started with finding the NMR spectrum. This was done by combining 0.35 milliliters of the unknown sample from vial 43, then combining that with 0.35 milliliters of deuterated chloroform, and placing that solution inside of the NMR spectrometer with a frequency of 90 megahertz to measure the spectrum. This figure here shows the spectrum for sample 99969 and sample 05024. So NMR yields two important pieces of information: the number of H atoms present, the number of peaks, and the relative numbers of each type of H group, the ratio of the areas shown here. This can be found using the NMR spectrometer or estimated by hand. So for this experiment, we were given a list of different possible compounds that our contaminants could be. Using this method of estimating NMR results by hand, we were able to get data points to compare our results to. Take CH3, CH2, CHO, for example. This is one H group, this is another, and then this is another. These groups are distinguished by what they are paired to, and an easy way to look at it is by looking at the molecular formula. The molecular formula can be split up into groups like this. And then this way we're able to see that there are three different groups or peaks, and now we're able to count the number of H atoms in each of these groups to find the ratio of areas. And the molecular formula once again helps us with this, because we can see that for this first group, CH3, there's a 3 in the molecular formula and 3 different H atoms in this group. This means that for the ratio of areas, the first number is a 3. And then by using this logic, we can figure out the rest of the ratio. There's 2 H's there, so there's 2. There's only 1 H in the last one, so it's 1. And by using this method, this entire chart was split out for all of these molecules. Now going back to the NMR spectrum for sample 99969, we were able to see from the graph that there are 2 peaks with a roughly 1 to 1.5 ratio. Using this information, we can narrow the options for 99969 down to paraxylene, which has 2 peaks, and a ratio of 4 to 6, which simplifies down to 1 to 1.5. All this information is gathered here in this table for all of the different unknowns. Now moving on to how the IR spectrum was found. First, drops of the unknown sample from vial 43 were pipetted on top of the window of the diamond ATR, and the IR spectrometer measured the data. This figure here shows the spectrum for sample 99969, and this chart shows the sample for 05024. So we can see that the IR spectra gives us a chart with dips. These dips, or peaks, indicate the absorption of the wavelength, proving the presence of a certain functional group. Each functional group has a certain range that they'll absorb from, shown here. And using the Lewis structures of the possible compounds in this chart here, we were able to predict the appearance of the IR spectra for each of the compounds, evidenced by this chart here. Each X represents the presence of a certain functional group in the corresponding compound, and should therefore have a peak or a dip in that region on the IR chart. So looking at the IR spectrum for sample 99969, we were able to see that there's a peak at 3019, which falls into the 3,150 to 3,000 range, indicating the presence of CH in benzene form. There's also a peak at 2,921, which falls into the 3,010 to 2,800 range, indicating the presence of CH, where the H is on a singly bonded carbon. There's another large peak at 793 that falls into an applicable range, 850 to 600 strong. This implicates the presence of CHCl, and this peak is known for not being entirely accurate with indicating CHCl, but instead a different group. So using the info from the previous slide, knowing that sample 99969 has CH on a benzene ring and CH on a singly bonded carbon, this could mean, using this chart here, that sample 99969 could possibly be benzene, mesitylene, or paraxylene. But we know that from our NMR data, the only match that 99969 has was with paraxylene. So this IR data further proves that sample 99969 must contain paraxylene. And all the IR data for all the unknown samples is gathered here in this table. Using all this data, it was able to be determined that the sample 99969 was most likely the compound paraxylene because of their match on the ratio of areas of the 1 to 1.5 ratio. Then a match on the number of peaks, 2 from the NMR data, and both molecules had the presence of a benzene ring and a CH functional group from the IR data. Sample 05024 was most likely the compound ethanol because of their match on the 1 to 2 to 3 ratio of areas, their match on the number of peaks, 3 from the NMR data, and both molecules have the presence of the OH and singly bonded CH functional groups. And sample 43 was most likely methanol due to the 3 to 1 match on the ratio of areas, their match on the number of peaks, 2 from the NMR data, and both of the molecules had the presence of the OH and singly bonded CH functional groups. So if the molecules discovered during this experiment are ever found in the drinking water supply, it can have many effects on human health depending on the one that was found. And besides just human health effects, there are many potential environmental effects as well. For this first sample, 99969, the presence of paraxylene in the water is a cause for concern and likely due to outside factors such as leaching from landfills, fuel spills, or industrial waste. Long-term health effects include damage to the liver, kidneys, and nervous system. And for the environment, aquatic life such as fish will experience high chronic toxicity. For the second sample, 05024, the presence of ethanol can be a result of many different contaminants such as industrial waste, fermentation by microorganisms, or agricultural runoff. Ethanol can exert a toxicological effect due to its effect on immunological functions, evidenced by feeling drunk when drinking alcohol, which is made up of ethanol. But for the environment, ethanol in the water can lead to hypoxia, which is low oxygen levels stemming from the overconsumption of oxygen by ethanol. For the last sample, vial 43, the presence of methanol in the water supply, unlike ethanol, is a cause for major concern. Even in small concentrations, methanol is highly toxic. If it is present in water, it can mean that the supply was exposed to industrial applications, fuels, or antifreeze. Long-term health effects include metabolic acidosis, blindness, nervous system damage, and death. And for the environment, if methanol is found, it can mean very bad things for the environment, particularly the aquatic life, and it can lead to death for most organisms living in the area. So to summarize, the goal of this experiment was to identify the unknown contaminants present in the 3 contaminated water samples using NMR and IR spectra. The presence of these molecules in drinking water would pose serious health risks, as evidenced by this discussion for both humans and the environment. Thank you.